begin our new lecture on the introduction to prestressed concrete. Please, any question in the previous lectures? Okay, if there are no questions, then let's begin today's lecture, which is on the introduction to prestressed concrete. This is lecture number 7. Topics included in today's lecture are introduction, the principle of prestressing, advantages of prestressed concrete, prestressing steel, high strength concrete used for prestressed construction, and methods of prestressing. At the end of this lecture, students will be able to explain principle of prestressing and classify methods of prestressing. This is a first slide on the prestressed concrete, which will develop your concept in prestressed concrete. You know that concrete is basically a compressive material with its strength and tension being relatively low. And for this purpose, we use reinforcing bars on tension side in our concrete members. You can see this beam, which is being subjected to 3-point loads. With the increase in the load, tensile stresses will keep on increasing, and if there are no reinforcing bars, then the beam will collapse very quickly and suddenly, because these cracks which will appear on the tension side will propagate upward very rapidly, and the beam will collapse and will be broken into 2 pieces. However, if reinforcing bars are inserted as we do in reinforced concrete, then these cracks which appeared in plain concrete would be restrained by the reinforcing bars. The condition is that reinforcing bar shall be properly bonded to concrete, and if this bond is perfectly intact, then reinforcing the strain in concrete and reinforcing bar will be equal, and the strains will be restrained by the reinforcing steel with high modulus elasticity and high strength. And the result is an increased capacity of reinforced concrete beam as compared to plain concrete beam. And you know that we provide reinforcing bars on the tension side. As you can see, a cantilever beam on the right top, and the reinforcing bars will be placed on the top side of the beam, because tensile stresses in a cantilever beam will be produced in the upper part of the beam. Okay, now if we can devise a mechanism, if we can use such a mechanism through which we can, for example, apply a pre-compression force on the tension side before the application of the load. If before the application of the load, the beam on the tension side is pre-compressed by some mechanism, let's say a steel wire is passed through the formwork, and then the steel wire is anchored on one side and stretched on the other side, and then it is kept in the stretched position. And if then concrete is poured inside, the steel wire which is in stretched position will be enclosed by the concrete. And when concrete attains its full strength, then if the wire is cut on both sides, so the wire, in its effort to regain its original length, will compress the beam, and the force will be transferred through bond between steel and concrete. So when the steel wire or bar tends to regain its original length, it will not be possible for the steel wire or bar because it is perfectly bonded to concrete and it is in stretch position. So as long as it remains in stretch position, it will keep on pushing concrete at the location where the steel bar has been placed. So if steel bars or wire has been placed on the tension side, it will apply a pre-compressed force. When the lower part of the beam is in compression before the application of the load, and when the load is applied, so this pre-compression which already exists will be completely or partially cancelled out, and the result may be a beam with no tensile forces on the bottom side if it is uniformly if it is a simply supported beam, and on top if it is a cantilever beam. So this is possible to produce a pre-compression force in the beam before the application of load. If we can do this, we can completely eliminate tensile forces in the beam or partially eliminate tensile forces. This is the concept. This is the concept of pre-stressed concrete. So it is called pre-stress. Why it is called pre-stress? Because the beam has been pre-stressed or pre-compressed before the application of load. So if any concrete member is pre-compressed or pre-stressed, pre mean before the application of load, is stressed, then it will be called as pre-stress concrete member. Okay. You can see in this figure, in the middle, the beam, which is pre-compressed, this beam is being, and then when the load is applied, the beam will either become completely straight, giving no tensile stresses, or there will be some tensile stresses within the limits. Okay, the principle of pre-stressing are explained in these two slides with numerically, with the numerical background and a numerical explanation. Let's say this is a beam. The first figure A. In the figure A, there is a simply supported beam whose depth is h, and the beam is being subjected to a point load W. You know that the bending moment diagram for this beam will be a triangular bending moment diagram with maximum bending moment occurring at the midspan. And if you draw the stress variation through depth of the beam, you know that you can do this using the flexure stress formula as long as the beam is in linear elastic range. F is equal to my by I will give you the flexure stress formula. Flexure stress formula will give you flexure stresses at any depth from the neutral axis, top and bottom. You know that flexure stresses at the neutral axis will be 0 because F is equal to my by I, and y is the depth from the neutral axis to the extreme top or bottom fibers of the beam. So when y is 0, F will also be 0. So flexure stress is 0 at the neutral axis, and when flexure stress is 0 at the neutral axis, at any other depth, flexure stress value can be plotted with the maximum values occurring at the extreme top and bottom fibers. You know that the top fibers will be compressed and the bottom fibers of the beam will be elongated or will be in tension. So when the top fibers are compressed and the bottom fibers are stretched, the maximum stretching and the maximum compression will occur at the midspan and in the extreme fibers. The maximum compression in the beam will occur because in the midspan, because bending moment is maximum at the midspan. And as you move from the midspan towards the support, the flexure stresses value will keep on decreasing till it becomes 0 at the support, because bending moment is 0 at the support. So in this way, you can plot flexure stresses variation through depth of the beam at any location and at any desired location, provided you know the bending moment from the bending moment diagram. If you know W, you can draw bending moment diagram. So M will be known to us, and the depth of the beam is H total depth. So Y at any location, if you want to calculate flexure stress, that can be easily calculated. You would know what is Y, so Y will be known to you. I is moment of inertia. So knowing M, Y, and I, you can calculate flexure stresses at any location. This is, let's say, it was a case of a beam, a reinforced concrete beam. However, if now we do not want to reinforce the beam, let's say we do not want to reinforce the beam, and we want to pre-compress the beam. So let's say before the application of load Q, the load Q has not been applied yet, and we pre-compress the beam by applying a force P, as shown in this figure. And how can this be done? As I said earlier, we can pass a cable through the formwork. We can anchor the cable on one side and stretch it on the other side, and then keep this cable in a stretch position, pour the concrete in the formwork, and when concrete attains its full strength, we will cut the wire on both sides And when the wire is cut on both sides, the wire will tend to regain its original length. And in this effort, it will start pushing. It will start pushing the beam, and this force P will be created by the stretched wire or cable inside the beam. And when this force P is applied on the beam, this will give rise to compressive stresses in the beam. And this compressive stress can be very easily calculated from this formula: F is equal to P divided by A. You know this because it's a favor compression force. This will give you compressive stress. Fc is equal to P divided by A. And A is the cross-sectional area of the beam. So Fc is equal to P by A. And all this happens before the application of load. So the beam before the application of load is in a pre-compression state of stress. In a pre-compression state of stress. In a pre-compression state of stress. Now, when the load is applied, when the load Q is applied, so in the same manner as we discussed in figure A, flexure stresses will be produced in the upper and the lower part of the beam. But since a pre-compression is already existing in the beam, so this flexure stresses which are produced by the load Q will be added to the already existing pre-compression state of stress. So a pre-compression state of stress, gives us a flexure stress equal to Fc and Fc on both sides, and the load will give us Fc and Ft, and this Fc will be added to the Fc. So the net compressive stress in the top fiber will be 2Fc, and the net tensile stress will be 0, because you already a pre-compression state of stress in the beam. And when the load would tend to produce tensile stresses in the lower part of the beam, this would not be possible because of Fc is already there. So this Ft has to cancel this Fc first, and then tensile stress will be produced. So with this, you can see that practically there are no tensile stresses in the beam if the pre-compression force has been applied in such a manner that it produced a compressive stress equal to the compressive stress and tensile stresses equal to the stresses produced by the load Q. So when the stress produced by the load Q is equal to the stress that you have already produced in the beam by applying a pre-compression force, then Fc will completely cancel out Ft with 0 stresses in the bottom fiber and twice the compressive stresses in the top fiber. So in this way, we have completely eliminated tensile stresses. So now there is no need of providing any reinforcing bar on the tension side. So in this way, we have completely eliminated the need for reinforcing bars on the tension side. So this is the concept of pre-stressing. Next, now we look at another situation where the pre-compression force is not applied at the centroid. In this figure B, the pre-compression force P has been applied at the centroid. In the figure C, the pre-compression force has not been applied at the centroid. Rather, it has been applied at an eccentricity E, which in this particular case is, let's say, h by 6. H is the total depth, and h by 2 is half the depth, and h by 6 is one third of this half. So 1/3 of the half depth, we apply force P, and the application of force P can be done in the same manner as I discussed earlier, by passing cable through the formwork, then stretching, pouring the concrete, and after concrete attains the full strength, release the cable. The cable will tend to regain its original length, and in this effort, it will push the beam in this manner. While in the previous case, the beam was compressed at the centroid, in this case, the beam has been compressed with some eccentricity. So in this case, the beam will also be subjected to some bending moment by this load, by the application of P. So P will produce not only the compressive stress, but also it will produce bending in the upward direction. The beam will slightly bend in the upward direction, and the bending moment value is P times E. P times E is the bending moment, and this bending moment is constant all along the length of the beam because you have P applied everywhere with eccentricity E. So the bending moment will be constant, and the bending moment diagram for P times E can be plotted very easily, and this will be a straight line like this. However, the bending moment due to the load 2Q will be still in triangular fashion like this, triangular shape in this manner. Okay, triangular manner. Now, in this situation, let's say what happens before the application of load. Before the application of load, P will also produce a compressive state of stress as was in the previous case. So this will be Fc is equal to P divided by A. But this pre-compressive force will also produce bending moment, and due to bending moment, flexure stress will be produced in the upper end, lower part of the beam. So in the upper part of the beam, there will be tensile stresses because the beam bends up. So the tensile stress will produce in the upper part equal to stress Ft minus Ft. And in the lower part of the beam, compressive stress is equal to Fc will be produced. So that the net effect of this pre-compression before the application of load will be this: Fc minus Ft, because Fc is already present, and this P will produce tensile stress is equal to this Fc. So this will be Fc minus Ft equal to 0, and Fc plus Fc equal to 2Fc. So this 0 and 2Fc state of stress already exists before the application of load. But mind that this state of stress exists at the mid-span, not at any other location. Then when the load 2Q is applied, so the load 2Q will produce this state of stress 2Fc and 2Ft at the mid-span, and you have already state of stress 0 and 2Fc due to the pre-stressing or pre-compression. So this 0 will be added to 2Fc, and 2Fc and 2Ft will be cancelled out. So you will have a 2Fc and 0 state of stress as was in the previous case. So with this, you can see that the difference between the previous case explained in figure B and that of figure C is that in the figure C, the pre-compression has been applied at eccentricity. So which means that eccentric application of pre-compression force may double the load carrying capacity of the member. Okay, as you can see that in this case the load is twice the previous load. Still you have the same state of stress as was in the previous case, which means that eccentric pre-compression is better than concentric pre-compression. Next, we discuss another case. This is a case of variable eccentricity. The force P has been applied in such a manner that it will produce no bending moment at the ends of the beam, and it will produce maximum bending moment at the mid-span. This cable, which was straight in the previous two cases, is now in this shape, in a curved shape. Okay, so when the stress is when the wire or cable is released, it will apply a pre-compression force here, and the bending moment will vary along the length of the beam because of this eccentricity. You have no eccentricity here, so P times E, this M is 0 here, and you have M is equal to P times E here. So in this case, the bending moment will be like this. You will have a bending moment. The bending moment will be like this. This is the bending moment. This. Unlike the previous case, you have a bending moment which varies along the length. In the previous case, the eccentricity was constant, and therefore bending moment produced due to pre-compression force was also constant. Here in this case, eccentricity varies along the length, so bending moment also varies along the length, and the bending moment will be maximum at the mid-span because E is maximum at the mid-span and 0 at the ends. Let's see what happens in this case before the application of load. Again, you will have a P divided by A, Fc. This Fc will be all along the length of the beam. This will be constant, and plus you would have maximum eccentricity at the mid-span. So P times E, which is the bending moment. The bending moment will will give us Fc and Ft and Fc. Ft in the top fibers and Fc in the bottom fibers. Okay, just like the previous case. So this Fc when added to this Ft will give us zero stress in the top fiber, and this Fc in the bottom will be added to this Fc at the mid-span of produced by the varying bending moment, and this will give 0 to Fc. So 0 to Fc will still be there because the bending moment at the mid-span is the same as in the previous case. However, the bending moment at the ends is not that of the previous case. The bending moment here is much less than the bending moment at the mid-span. So this state of state 0 to FC will not be same everywhere. This will not be same everywhere. Okay, this will not be same everywhere. However, at the midspan, this will be 0 to FC. Now, at the midspan, we can see that we will have a state of stress 2FC and 2FT produced by the load. So it will give us F2FC and 0 as it was happening in the previous case. However, at the ends of the beam, at this location, you have only FC and FC, and you don't have any tensile stresses and compressive stresses at the ends of the beam, neither due to the load nor due to the pre-compression force. So you will have a pre-compression stress, compression stress at the ends of the beam. And between this location and this location, there will be a change in this state of stress from 2FC to 0. 2FC will keep on decreasing, and from 0, the FC value will keep on increasing. So you may have, for example, at this location, you may have a value equal to 1.5 FC, but on the bottom side, you may have a compression equal to 0.5 FC. This 0.5 FC will keep on increasing, and 2 FC will keep on decreasing till it becomes FC and FC at the ends of the beam. Okay, so in this case, the state of stress will vary along the length of the beam. However, you can see that no tensile stresses are produced anywhere in the beam. Now, the last situation. In the last situation, let's see, we reduce the load from 2Q to Q. Okay, we reduce the load from 2Q to Q, and everything remains the same as it was in the previous case, case D. So at the midspan, you have 0 to FC state of stress as was in the previous case, but due to load Q, now you don't have 2FC. This is only FC and FT because the load has been reduced. Okay, so this FC will be added to this 0, and it will give us FC, and FT minus 2FC will give us FC. And at the end, it will be FC. So you can see that the state of stress remains the same all along the length of the beam, and the beam remains in a state of compression all along the length of the beam, and this compression is constant along the length of the beam. So this is, for several reasons, a much better situation than all the cases, because we have a state of stress which is constant along the length of the beam. So you can use same strength of concrete and so on. Okay. The important conclusions that we draw from the previous several examples. Prestressing can control or even eliminate concrete tensile stress for specified loads. You have seen this. Eccentric prestress is usually much more efficient than concentric prestress. We have already seen this. And variable eccentricity is usually preferable to constant eccentricity from the viewpoints of both stress control and deflection control. One thing that I forgot to tell you that not only the tensile stresses, but the deflection can also be completely eliminated by prestressing technique. And prestressing results in the overall improvement in performance of structural concrete used for ordinary loads and spans, because one of the major problems in reinforced concrete is that when the span is very long, then you will have to use much deeper members, and this may make the reinforced concrete members uneconomical, very heavy members, even very heavy to take its own load. Therefore, and the heavy members in reinforced concrete members are required in order to minimize deflection. So as you have seen in this case, that prestressing can completely eliminate the deflection and tensile stresses. We can use much economical cross sections in the prestressing members, even for longer spans as compared to reinforced concrete. Objectionable deflection and cracking, which would otherwise be associated with the use of non-prestressed reinforced concrete at high stress, are easily controlled by prestressing. These are all advantages of prestressing. You have seen this. Okay, if you have any question now, you can ask your questions. Otherwise, we will go ahead with the next slides. Any question? Any question? Okay, if there is no question, so let's go ahead with further explanation of pre-stressing. Uh, as I said earlier, that usually wires and cables are used for pre-stressing. So let's say we now discuss uh, what type of pre-stressing steel and or wires shall be used for pre-stressing. Uh, this is a farm work. Is a farm work where the length is LC of this farm work. So the length of concrete member which will be produced in this farm work will also be LC. LC unstressed length of concrete. LC, so C stands for concrete. This is length of concrete member, because when you pour concrete inside this farm work, this will give you the same length as the length of farm work. Okay, now let's say we have a steel bar equal to LS, and what we do is that we keep this bar in the farm work before concrete is poured, and we stretch this. We stretch this bar up to a certain strain, but mind that this strain shall not be more than the yield strain. Because if it is more than the yield strain or even closer to the yield strain, then the steel will permanently set, and it will not be possible for the steel to regain its original length. And if it is not possible for the steel to regain its original length, it will not uh, produce the pushing force. The pushing force cannot be produced by a permanently stretched member. Okay, so let's say if it is a grade 40 steel, so for a grade 40 steel, we will stretch the steel up to 30 ksi, because the yield strength is 40 ksi. So we will stretch the steel up to 30 ksi yield strength, and then we will release. Okay, now first of all, let's say the steel bar is in a stretch position, and we pour concrete. That when concrete gains its original, when concrete attains its full strength, then the steel rod is released from both sides. So then the steel rod, through the bond between steel and concrete, will tend to uh, push concrete, because the steel rod is in stretched position, and it will tend to regain its original length. And if it does not succeed in regaining its original length, it will keep on pushing the concrete member. However, the steel, the concrete member, the concrete, concrete shrinks in the creep with time. The effect of shrinkage and creep of concrete will also reduce the length of the concrete member, and the steel, which is in stretch position and is perfectly bonded with concrete, the length of the steel bar will also decrease if the length of the concrete member decreases due to creep and shrinkage. And any decrease in the length of steel means a loss in the pre-compression force, because the pre-compression force was due to the stretching of the steel. So with the reduction in stretching, or with the reduction in the length of steel, because then the steel succeeds in regaining its original length. So if steel succeeds in regaining some of its original length, then the pre-stress of equal to that amount will be lost, and it will not be a good situation, because we should have a pre-compression force applied throughout the life of the concrete member. Okay, what is the amount of this strain that we can produce in a grade 40 steel? As I said earlier, that a grade 40 steel can be conveniently stretched to a stress level of 30 ksi. So the strain associated with this will be equal to 1.03 in 10 to the power minus 3. And the steel elongation in terms of delta will be equal to 1.03 in 10 to the minus 3 multiplied by the length of the steel. This is the maximum delta that can be produced in a grade 40 steel, because it cannot be stretched beyond this limit uh, uh, for the concern, due to the concern that steel may permanently set. So in order to avoid this situation, in order to avoid permanent setting of the steel bar, we will not stretch the steel even closer to its yield limit, which is 40 ksi. So this is the maximum delta that we have produced. Now, the shrinkage and creep will reduce this delta, because the shrinkage and creep will cause reduction in the length of the concrete member. And since steel bar and concrete are perfectly bonded, any reduction in the concrete member will also reduce the length of the steel. Okay, the shrinkage will reduce the length, but creep is a phenomena which occurs in concrete at constant load or stress. So there is a constant stress in the form of pre-compression stress applied at both ends of the beam. This will further compress the beam, and due to the creep effect, the reduction in the length of the member will also occur. But this reduction in the member, concrete member, will not occur alone. It will also decrease the length of the steel. And any reduction in the length of steel means a loss in pre-compression. So if this, it has been noted that shrinkage and creep together will be producing a strain equal to 0.9 in 10 to the power minus 3, roughly speaking. So if a strain equal to 0.9 in 10 to the power minus 3 into LC is produced in the opposite direction, so you can see that the stretched delta was 1.03 into 10 to the power minus 3 LS. Okay, and the strain in the opposite direction to this is 0.9. It's almost equal to this. So after concrete reduces by this much strain, it may completely eliminate the already stretched position of the steel bar, which means a complete loss in the pre-compression. So we can see those now that the final, what is the final stress left with us? Because the stress was produced to strain, and we have seen that the opposite, the strain in the opposite direction has occurred due to shrinkage and creep equal to 0.9 and 10 to the power minus. So finally, the strain left is 1.03 minus 0.9 10 to the power minus 3. When this is multiplied with the modulus velocity, so we'll be left with only 4 ksi stress, which was initially 30 ksi. And this will further reduce due to the elastic shortening. You would have seen and you would have learned that when a load P is applied on a member whose length is L and area is A and modulus velocity is E, so elastic delta compression if P is in compression, and elastic elongation if P is in tension will occur with time. Will occur instantaneously, not with time. It will occur instantaneously as soon as the P is applied. So this delta will further reduce the strain, and finally you may be left with 0 ksi. Okay, what is the solution to this? The solution to this is that low strength steel bars cannot be used for this. If we can increase the yield strength of steel up to 200 ksi, for example, then we will be able to stretch the steel up to a stress limit of, let's say, 180 or 150 ksi. So the strain will be more, and then that strain, if creep and shrinkage gives us a strain of 0.9 in 10 to the power minus 3, and if there is some delta, then the strain produced in the steel minus all the recovered strain will be deducted. Still, we would be having some stress. So let's see now if we can use a initial stress of 150 ksi in a high strength steel. We are using a high strength steel wire or cable. So in this case, the strain produced will be equal to 5.17 in 10 to the power minus 3. If this 5.17 in 10 to the minus 3 is deducted, the shrinkage and creep strain is deducted from 5.17. So we will be left with the strain, which will be still much higher in the previous case. And then when this is multiplied with E, we will still have 124 ksi left in the steel bar, which was initially 150 ksi. And 124 ksi is also a substantial value of stress for the pre-compression, unlike the previous case in which there was a complete loss of stress. So the conclusion from this discussion is that we can only use high strength steel wires, cables, or bars for pre-stressing. There are 3 types of high strength steel available in the market. Some are wires are generally available, and they can be bundled. 1 wire, 2 wire, 3 wires, and any number of wires can be used for pre-stressing. Usually wires not more than 50 are used at one and the same time for prestressing. Then we have a stranded cable. Stranded cable is fabricated with 6 wires wound around a seventh of slightly larger diameter. So this gives us a stranded cable. Cables are also available in the market, and then bars are also available in the market, but usually these steel bars are not used even if they are high strength. They are not used for prestressing. Generally, cables and wires are used. Wires are normally used in the precast industries, जहाँ पर तैयार छतें वगैरह बनाते हैं तो उधर वायर्स इस्तेमाल करते हैं, और केबल स्टैंडर्ड केबल्स आर यूज्ड in the post tensioning in the bridge girders or similar structures. The diameter of the bars available and the wires available is this range, but this is not necessary that you will get always these diameters in the market. Maybe there are different diameters in the market. These are generally available in the market. Pre-stressing wires 5 to 7 millimeter and strands up to 15 millimeters are available in the market. Alloy steel bars up to 35 millimeter and 32 millimeters are also available in the market. The yield strength of these wires, the yield strength up to 235 to 40 to 50 KSI in round wires available. The strand 7-wire strands are available in 250 and 270 KSI. In Pakistan, the most common is 270 KSI strand, 7-wire strands, which is available almost everywhere in the market, in good market. The stress strain curve for the pre-stressing wires and cables. Generally, unlike the mild strain, grade 40 and grade 60, the stress strain curve is not very clear in the case of high strength steel, wires and cables, and it becomes difficult to exactly determine the yield strength of high strength steel. For this reason, the ASTM has given us a guideline, and which says that on a stress strain curve, draw a line equal to 1% of the strain parallel to y-axis, and wherever it meets the stress strain curve of the high strength steel, it will be the yield strength. It is important to note that the exact determination of the yield strength is very important, because if the steel wires or cables are stretched even closer to the yield strength, there is a possibility that they permanently set, and permanent setting will give us then no stretching. So it is important to calculate the yield strength very accurately, and this can be done by testing a steel wire or cable in the lab, and then drawing a stress strain curve for the wire or cable, and then according to the ASTM, 1% at 1% strain, a line will be drawn parallel to the y-axis, and this line, wherever it meets, it will be your yield strength. In the case of strands, for alloy steel bar, it will be 0.7%. So in this manner, we can determine the yield strength of wires and cables. You can also see that prestressing steels have significantly less ductility as compared to grade 40 and 60 mild steel bars. But unlike reinforced concrete, ductility is not an objective to be achieved in prestressing steel, because you have seen that there is complete elimination of tensile stresses and deflection. So we avoid the occurrence of tensile stresses in the beam. For this reason, we don't want to it is not our purpose in the pre-stressed concrete to achieve a ductile mode or ductile behavior of the beam. Okay, the modulus of elasticity varies. For strain, it is 26 to 27,000 psi, KSI, and for round wire, it is 29,000 KSI, and for elastic bar, it is 27,000 KSI. So it varies from 27 to 26 to 29,000 KSI. If there is any question, you can ask your questions now. If there are no questions, you can go ahead. Any question? Okay, if there are no questions, we will take a 10 minutes break and then we will continue after the break.
सर लीव कर दे सर हम।
Okay, so let's now discuss the next topic in pre-stressing steel, which is relaxation. When pre-stressing steel is stressed to the levels that are customary, and customary means that are common during initial tensioning and at service load, it exhibits a property known as relaxation. Relaxation is defined as the loss of stress in the stressed material held at constant length. You have seen in the previous examples that when a steel wire or cable is stretched, so as long as it is in the stretch position, it will tend to regain its original length, and in this effort, it will exert a compressive force on the concrete member, and this compressive force will produce compressive stresses which are beneficial for the concrete member in terms of load carrying capacity of the member. However, if there is a if steel if steel wire or cable succeeds in regaining its original length partially or fully, there will be a loss in yeah, stress, recompression stress, and if there is a partial or full loss of recompression stress, there will be also a loss in the precompression, and loss in precompression will then completely uh, reduce or eliminate the beneficial effects of recompression. So it is important for the concrete member to remain in a pre-compression state of stress, and for this it is necessary that steel shall be in a stretched position, and any recovery or regain in the length of the steel will cause a pre-stress loss. So with high strength steel wire or cables, this loss in strain and then further loss in stress will be in the allowable limits. So high strength steel wires and cables are usually used in the pre-stressed concrete. However, there is a this is a property of steel which is called as relaxation. This occurs at the in the stretched position, even if there is no decrease in the length of steel, which means any no recovery in the length of the steel at constant length. Let's say we produce a delta equal to 2 inches. So even if steel is in this stretch position without any loss in the length of steel, or without any loss in the stretch position of the steel, to be exact. So without any loss in the stretch position of the steel, there will be a loss in stress. There will be a loss in stress, and this is a property of steel. This occurs when the steel is stretched for a long time. When the steel is stretched for a long time, then there will be some pre-stress stress loss, and this occurs at constant strain without any change in strength. Without any change in strain, without any change in strain, at constant strain in stretch position, there will be a loss in uh, stress, and this loss in stress at constant strain is called relaxation. It is property of steel. And the same basic phenomena is known as creep when defined in terms of change in strain of a material under constant stress. Creep, creep occurs when a concrete member is kept for a long time under compression or under tension. So it will cause, in the case of compression, a reduction in the length of concrete member, and increase in the length of member in the case of tension or stretching. So unlike a creep, because creep is a phenomena occurring at constant stress, and the relaxation of steel is a phenomena which occurs at constant strain. So in this term, they are somehow similar phenomena. One occurring in at constant strain, relaxation occur at constant strain. Stress loss at constant strain and creep occurs at constant stress. Strain occurs at constant stress. Okay. To be specific, if a length of prestressing steel is stressed to a sizable fraction of its field strength, say 80 to 90%, and held at constant strain between fixed points, such as the ends of the beam, the steel stress will gradually decrease from its initial value FPI. This can be, however, calculated using this equation. This is an equation in terms of log. FP is the stress which will be left after the after relaxation. FPI is the initial pre-stress force stress applied, and the log of TT is the time in hours after which we want to know how much loss is occurred due to relaxation. FP is again the final stress after relaxation. FPY is the yield strength. So if you want to calculate the pre-stress loss due to relaxation after 400 hours, so this log T will become log of 400. And if let's say FPI for a 270 KSI, this initial is let's say 200 KSI, and so this will be FPY is 270 KSI, FPI is 200, initial stress yield is 210. You are only left with one unknown, which is FP. FP is unknown. FP can be calculated because you have FP on the right as well as on the left side. So further simplification of the equation will give you the pre-stress after relaxation. Okay, after it will be less than FPI, the initial pre-stress. So in this manner, you can calculate the stress loss after relaxation. Okay, as you have seen in the previous several examples and slides, that a pre-compression force is applied, which may be sometimes very, very high. For this purpose, we would like to use high-strength concrete in our pre-stress members. And it is true that generally we use high-strength concrete in our pre-stress members. And there is no exact definition of high-strength concrete. However, usually concrete having a cylinder strength of 8,000 and above are called as high-strength concrete. Although sometimes it is possible that we use an ordinary strength concrete in pre-stress members, depending on the situation. High-strength concrete can be made using carefully selected but widely available cement, sand, and stone, and certain admixtures, including high-range water-reducing superplasticizer, fly ash, and silica fume, plus very careful quality control during production. I hope you have studied these things in your concrete course. The advantages of high-strength concrete are that high-strength concrete has a higher elastic modulus than the low-strength concrete, so that loss of pre-stress force resulting from elastic shortening of the concrete is reduced. Creep and shrinkage losses are also low, and high bearing stresses in the vicinity of tendon encourages for post-tension members are more easily accommodated. This sentence refers to a situation where when a high-strength steel wire is cut on both sides, so it will push the concrete, and this was a situation which I explained in the beginning. In this situation, you would have observed that the steel is stretched before concrete is poured. The steel is in stretched position and concrete is poured. When concrete attains its full strength, then steel is cut on both sides. Okay. This pre-stressing can be produced in another manner, which we will discuss in the coming slides in detail. But let me explain it a little bit also right now. That it is possible to keep a conduit inside the formwork, conduit made of plastic or aluminum or some other material, a conduit, a pipe inside the formwork, and then the cables or wires are passed through this conduit, and then concrete is poured without steel wires or cables being stretched. So when concrete is poured, you know that there is a conduit or pipe inside the formwork, So although the pipe will be bonded to the concrete, steel wires inside the pipe will not be bonded to the concrete member. Now, when concrete attains its full strength, then the steel wires is anchored on one side of the member and stretched from another side of the member, and then anchored on both sides with the proper anchorage devices. So the pre-stressing force is transferred through the anchorage devices on both sides, not due to the bond between steel and concrete. This kind of technique is called post-tensioning. Why this is called post-tensioning? Because the steel wires or cables are stressed after concrete attained its full strength. Unlike the previous case in which the steel wires or cable was stretched before concrete pouring. So when steel wire is stretched before concrete pouring, this will be called as pre-tensioning. Pre-stressing through pre-tensioning of wires. And when steel wires or cables are stretched after concrete has attained its full strength, then it will be called as post-tensioning of steel wires or cables, uh, post-tensioning. So it will be called as post-tensioning technique and pre-tensioning techniques. Uh, Both are used in pre-stress concrete industry. So in the post-tensioning, high bearing stresses in the vicinity of tendon anchorages is, is very obvious. It will occur. So this can also be easily accommodated in high-strength concrete. In the case of pre-tension elements, higher bond strength results in a reduction in the development length required to transfer pre-stress force from the cables to the concrete. In the pre-tensioning technique, the pre-stressing force is transferred through bond between steel and concrete. So the bond between steel and concrete will be good if we use high strength concrete. Finally, concrete of higher compressive strength also has a higher tensile strength, so that the formation of flexure and diagonal tension crack is delayed if there is any. The stress strain curve of high strength steel, of high strength concrete. You can see there are many curves of high strength concrete, and with the increase in high strength concrete, the ductility, comparatively speaking, decreases. The typical set of compressive stress strain curve for normal density concrete obtained from uniaxial compressive stress performed at normal. High strength concrete are more brittle than normal uh, concrete, ordinary strength concrete. You can see. However, as you know that brittleness of concrete is not an objective in to be achieved in reinforced either in reinforced concrete or in the pre-stressed concrete. But comparatively speaking, the higher the strength of concrete, the more brittle it will be. Okay, now finally coming to the techniques which are used for pre-stressing. As I said earlier, there are two techniques, pre-tension and post-tension techniques. In pre-tensioning procedure, the strands or cables are tensioned over the full length of the casting bed at one time, as I said earlier, after which a number of individual members are cast along a stress tendon. When the jerking force is released, the pre-stress force is transferred to each member by bond and the strands are cut free between members. Like this. This is a typical bed of a pre-stress precast industry. You can see a wire being placed in the formwork, and the wire is anchored, but this anchoring is done to the one side of the bed, not to the side of the concrete member. So it is anchored on one side, the wire has been anchored on one side and has been passed to the formwork, and then with the help of a jack, this wire is stretched, and then it is kept in the stretched position, and concrete is poured inside the formwork. When concrete achieves its full strength, then wire is cut from both sides, and wire through bond between concrete and steel will transfer the pre-compression force to the member. Okay, this is the case of a concentric pre-stressing. You can also produce varying eccentricity pre-stressing by holding down the pre-stressing wire or cable in this manner, and the rest is the same. Multiple girders and beams can also be produced at one and the same time in a precast industry. By this means, you can see that anchorage, the wire or cable, the wire is anchored on one side, and then the wire is passed through all this farm work. Okay, the wire is then stretched with the help of a jig and then kept in the stretch position. Concrete is poured in all these beams, and then the wires are cut from this side also in this separator between the two girders, also from this side to this side. And when the wires are cut on both ends of every beam, the pre-stressing force will be transferred uh, through bond between steel and concrete. This is a technique of pretensioning. Okay, these are some pretension girders, I girders, T girders. The advantages of pretensioning are that they are very well suited to the mass production, which means that if you want to reduce a large number of beams at one and the same time, you can use this as we have seen in the previous slide. And pretensioning is a particularly economical method of pre-stressing, not only because the standardization of design permits reusable steel or fiberglass forms, but also because the simultaneous pre-stressing of many members at once result in great saving of labor. However, this pre-tensioning technique can be used only in the controlled environment, like in the factories, because the steel has to be in a stretch position for a long duration, maybe for 7 days or 15 days, because the steel must remain in stretch position until concrete attains its full strength. So for this purpose, the jig will be engaged, the anchorage devices will be engaged, the steel will be in stretch position. So it will be dangerous to keep steel wire and cables all at the site. So for site job, pre-tensioning is not recommended. Pre-tensioning is recommended, and it's a good technique in factories and industries in a controlled environment. For the job, post-tension technique is much better. In the post-tensioning process, usually hollow conduits containing the unstressed cables or wires and tendons are placed in the beam forms to the desired profile before pouring the concrete. The conduit is wired to the auxiliary beam reinforcement to prevent accidental displacement, and the concrete is poured. When the concrete has gained sufficient strength, the concrete beam itself is used to provide the reaction from the stressing jig, like this. Okay, this is the formwork, this is a conduit, and with through the conduit, the cable is being passed and before the pouring of concrete. Now, when the concrete is poured, the pipe or the conduit will be bonded, no doubt, to the concrete, but the cable inside the pipe will remain unbonded. And then, when concrete attains its full strength, the cable will be anchored on one side through an anchorage devices, and it will be stretched on the other side from the other side through some jacking assembly. And also, after that, the jacking assembly will be removed, and it will be anchored through anchorage device on the other side as well. So the pre-compression force will be transferred to the concrete beam through this end bearing and anchorage devices from this side and this side, unlike the pre-tensioning. However, it is possible sometimes to even inject some grout inside the pipe, and to make this tendon is cable is bonded tendon cable after the stretching and after the force has been applied, it is possible. Okay, these are some anchorage devices, and these are anchor blocks, and these are wedges depending on the number of cables and tendons. These can be obtained from the market. You can see conduit being placed inside the girder. Okay. Change in the uh, size of the anchor devices, but this will be very nominal, and that can be also taken into account in the design of pre-stressed members. Next, I will show you a video now.
We'll explain the entire process of producing a pre-stressed concrete unit at a pre-stressing plant. In this case, a double T. A double T is used primarily. This video will explain the entire process of producing a pre-stressed concrete unit at a pre-stressing plant. In this case, a double T. A double T is used primarily in parking structures, but can be used in virtually any type of building, including office buildings, industrial buildings, and schools, to name a few.
Double Ts are kind of a unique product with having a capability of having a very long span. When you start talking long spans, you're talking 60 feet plus, and sometimes goes as high as 120 feet.
The typical day of a pre-stressing plant usually starts very early in the morning. The product from the previous day's casting has cured by now, and the pieces need to be stripped from the form to get ready for today's casting. For any pre-stressing plant, it is very important to maintain a clean plant. Maintaining neatness is not only positive from an image standpoint from the day before, could create a tripping hazard or other safety problem. The first part of the process is setting up of the form. A thorough cleaning of the entire form is done with basic labor and appropriate cleaning equipment. Setting the side forms, or in the case of a typical double T, the forms may be fixed forms with an appropriate draft to allow for easy stripping. Once the bed is cleaned, it's ready for setting up today's cast. This particular bed is set up for 5 double Ts, each about 60 feet long. The bed has a total length of 400 feet. This is a self-stressing form, where the form itself is designed to take the total pre-stress force and compression, and also to handle the eccentricity of the strands. Sometimes the producer may use a form that is set between bulkheads that are built right into the ground. The pre-stressing force is then resisted entirely by the bulkheads and their foundations. Next, the strands are placed in the form and extended from end to end. Crew members thread the strands through each of the dividers and then run them through the stressing plates at each end. The typical spacing of the strands is approximately 2 inches. This divider is a steel device that separates the individual double T units from one another. A gap of about a foot is typical between the ends of the adjacent pieces. This gap is required so the strands can be accessed and cut, and that each double T can be stripped from the forms. The next step is the tensioning of the strands. In this case, we have a strand pattern with straight strands of 6 strands in each stem, as shown here. The strands are first tensioned to about 2 to 5 kips based on the gauge pressure reading. In this case, a mark is made on the strand after the preload is applied. The strand is then tensioned to the specified level and is measured using the gauge pressure on the hydraulic pump. The QC technician then checks the elongation against the theoretical elongation. The requirement that is the force on the gauge and the elongation must match within 5%. If that tolerance is not achieved, the reason must be established and the strand may have to be detensioned and retensioned. After the strands of this double T are all stressed, the remaining embeds are set in place. These include stem reinforcing, lifting devices that will be used to strip and handle the piece, forms for blockouts in the flange, and forms for blockouts in the stems, flange reinforcing, and flange connectors or vectors along the edges. In this case, One of the double T's in the bed has typical flange connectors applied along one edge and special flat plate connectors applied along the other edge to accommodate connections across an expansion joint. The form is now ready to have concrete poured, but only after a pre-pour quality control check has been made and the QC person signs off on it. This QC check can also be done by the bed superintendent and depends on the particular plant's practices. Either way, the check is critical to ensure an end product with the highest quality.
There's always things you look for. The mesh, you look for anything that could be touching the stems on the bottom, like any wire ties that might have fell in there, because that would develop some type of a spot. You check the length. You want to make sure that the damps are correct. Do we have the strand stripped properly? So there are a lot of critical areas that you need to verify.
Concrete is mixed at the batch plant under tightly controlled conditions. The cement is supplied using tanker trucks. Here, the cement is being blown from the tanker through piping to the cement silos. When needed, aggregates are delivered to bins in the batch plant. The aggregates are stored outside of the batch plant in separate bins. In this case, an enclosed vertical bin system is utilized. During winter, in northern climates, the aggregates must be heated to get them to flow properly through the batching system and to maintain proper concrete mix temperatures. Payloaders are used to shuffle the materials to the conveyor belt. Computers are used to proportion the materials for the desired concrete mix. Cement, sand, stone, water, and admixtures are measured according to signals from the computer. After the concrete is mixed, it is discharged into a delivery device. It's imperative that the concrete mix be delivered to the form as soon as possible. These vehicles are called tuckers, and they are used to deliver the concrete to the bed in the yard. A self-consolidating concrete is being used to cast these particular double T's. With this type of concrete, vibration is not required to consolidate the concrete. However, minor controlled vibration is used in the double T stems to help remove air from the sides of the form, reducing bug holes in the stems. There are many advantages in using this type of concrete.
We do use self-consolidating concrete for our double T's. We feel that it gives us a better finish. We feel that it's easier to place, takes less labor, less strain on labor to place that concrete.
The QC department will make the necessary tests at this time, including a temperature check of the concrete. Since SCC is being used here, a spread test is done to check the concrete flow in lieu of a slump test. The spread is measured to assure conformance to the planned spread. The edges of the circle of concrete are also inspected to check for segregation. The appearance is translated to a visual stability index number. There is a check for air content. Cylinders are filled and will be used later for strength tests of the cured concrete. Back at the bed, the concrete placement continues. A vibrating screed is used to level the surface evenly. A bull float is used to finish the surface. An evaporation-reducing spray is also being applied to the surface to minimize the potential for plastic shrinkage cracking. The final finish will vary depending on the use of the double T. If a cast-in-place topping is necessary, the surface will be made very rough so that a good bond will be achieved. If it is a roof, the finish will be relatively smooth, but not necessarily perfect. In this case, the surface is broomed as these double T's are being used in a parking structure. Different patterns can be applied depending on the needs of the project. The bed is now in its curing stage. Sometimes, particularly in cold climates, the double T may be covered with tarps. In other areas, they may be open. Accelerated curing is often done using live steam or radiant heat from heaters attached to the form itself.
Double T's for parking garages really need to be held to a high standard. When they're assembled in a garage, they make the finished surface. There are tolerances for putting these pieces together, offsets in the surfaces. All of the connections are very sensitive as well to be executed properly. The embedments in the double T have to be placed properly. So the
12 to 16 hours of curing, the tees are ready to be stripped. The QC department first tests the concrete to be sure it has achieved the strength required to detension the strands, typically 3,500 psi. This is a typical test being conducted. The strands are detensioned in a specific sequence established by the QC department or the plant engineer. Here, personnel are positioned at each end of the bed and at some of the intermediate bulkhead locations. On a signal, they burn the strand at each end. After all the strands are cut and block-out formwork has been removed, the tees are stripped from the form. Cables are attached to the lifting devices, and each piece is removed and transported to a detailing area for any minor cosmetic touch-ups. Also at this time, the QC department does a post-pour QC check on each piece that is brought to the detailing area.
When I first get back there, I go and check the length of the piece, verify that within, there's a tolerance of probably a quarter inch or so. Check the width, we check the vectors, we check the electrical blockouts. I do a visual for any type of discoloration in the stems underneath the piece, any type of surface cracks, bug holes, just do a complete visual.
Any defects are noted so that repairs can be done before shipping the tee. After all the work is completed, the double tees are moved into the storage area where they are typically stacked using appropriate dunnage located near the ends. When the job site requires the tee to be shipped, it is loaded on a trailer and transported to the job site. What you have just observed is the process for making one type of pre-stressed product. These other types are made using essentially the same process. Hollow core plank, which are used for floor and roof components in multifamily housing, schools, hotels, and many other buildings. Inverted T-beams, which can be used in any total precast concrete build system. Columns, which are cast horizontally and then rotated in the air at the job site. They are often designed as pre-stressed components. Architectural spandrels used in office buildings and parking structures can be made using the pre-stressing process. Deck slabs and box beams, which are used primarily in short span bridge construction. Standard ashtoe girders, which are used in long span bridge construction. Standard bulb tees are also used in long span bridge construction. Pre-stressed piles that support any type of building in areas that have unfavorable soil conditions. As you can see, there are many types of pre-stressed products available. The variety of products that can be pre-stressed in a long line operation is almost unlimited and is up to the imagination of the design professional.
We really do encourage our customers and architects and engineers to get to our plants to really understand how precast concrete is made. They need an understanding of the high quality that they can get out of precast concrete as opposed to the random quality that you might get out of cast in place concrete.
Well, it's important that we do things as efficiently as we can and as cost effectively as we can, but also as well as we can. And it's not only my responsibility, but the responsibility of everybody here, management, labor, everybody included, to do the best job that they can to, at the end of the day, make a little bit of money, but also have a customer that's very happy and will possibly want to have some return work coming back our way.
Okay. This was a video on pre-tensioning. Next, I will show you a video on post-tensioning. In the beginning, there are several anchorage devices shown in this video. Several anchorage devices are shown. These are anchorage devices. Okay, these are a few pictures from the BRT project. You can see a girder being prepared, post-tension girder, and post-tension cables have been routed. You can see strands at 5 levels have been used to apply this pre-compression force in this girder. Okay. This is the end of the lecture. If you have any questions, you can ask questions. Otherwise, the lecture is over. Okay, any question? Anyone? Any question? Okay, if there are no questions, you can study this lecture or other lectures also, and you can come up with your questions next time. Okay, today's lecture ends with this slide. Okay, thank you very much. I hope we can discuss next topic in the next week and also answer some of your questions. Okay, thank you. Assalamu alaikum.